Hi and welcome to this video about access masks. So in this video I want to describe what access masks are and where do they appear in Windows. So first, what are access masks? The basic idea is that it's a way to represent the access rights for a particular object in a compact form. It's really a 32-bit value that has various bits with various meanings, which we'll see very soon, and they represent what anyone can do with that thing this access mask represents. Usually this is stored in one of two locations. One of them is a handle. So every time I open a handle to an object, at least I try to open a handle to an object, I have to specify what kind of access I'd like to get. And this is specified using this access mask, which means that if I am to get that access mask, I should be able to pass some security checks. If that works, then that access mask will be stored in the handle as part of the handle, which means that even if I have multiple handles that point to the same object, not all handles are the same. Some handles are more powerful than others, depending on what the access mask that was used to open that handle. Also, access masks occur in access control entries or ACEs, which are part of a larger structure called the access control list or ACL, which specifies who can do what with the object. So the what part is represented by ACEs. By access masks, which are stored in these ACEs. And so this is where these access masks are really stored. And technically the way we use them in practice is when we try to gain access to some kernel object. So let's take a look at some tools and then we'll dig some more into the details of access masks. So first, if you open something like Process Explorer, if we take any process of interest, we can look at the handles for that are part of this process as part of the handle table for the process. And each handle has a bunch of properties. So we see the handle value itself, the type of object it points to indirectly, the name of the object if it has any, and then we get to the access. The access is the access mask. So this is a bunch of bits that together correspond to some 32-bit value representing the kind of access this handle has to this particular object. In this little example, it's some unnamed event. It doesn't matter. But then there's a decoded access column here that shows you in a textual form what that access mask means. Because the access mask is just a number, so you have to go to the Windows headers to figure out exactly what each bit means. So to make it easier, we have this column, which in fact I added almost 10 years ago to Process Explorer, and this gives you a textual representation of what that access mask is, so I don't have to go and hunt for the actual bits in the Windows documentation or header files. So in this case, this event object, this particular handle has event all access, meaning it can do anything it wants with that event object. Here's another example, some kind of file being opened here using this handle. This particular file handle has that particular access mask. These are the bits, that's the actual number. And then you can see here the decoded access means synchronize and execute, which means we can run this file, we can execute this file if it's a kind of a PE. In case of directory, it means we can actually list items in the directory. And synchronize means that we can wait on the object until it becomes a signal, whatever that means for that object. In this case, for a file, it means that some kind of maybe asynchronous operation might have been completed. So in any case, for each object type, obviously there's some specific aspects for that object type, and there are some generic things like read control. So all these things have to be somehow represented as part of the access mask and should have some way to specify these kinds of things when we're writing code. And so that's one way to see what is happening here in case of handles. By the way, when we double click any one of these handles, what we see here are properties for the object, not the handle itself. So nothing here is specific about the handle, it's really about the object. The handle properties are right there on this line. So here's another example for a key object. So this key object is a registry key open for read control and key read access only, which means if someone tries to write to this registry key using this handle, this will fail with access denied, because this handle has no such powers. It can't really do that. So this is one way of looking at it. Another way is to look at the access control list that I mentioned. So the way to see that using Process Explorer or other tools that show the classic security dialog in Windows. So if we find something that actually allows us to see what's going on in the security tab, and of course we can go and see these kinds of things in the Explorer, for example, because it's a standard dialog. So here's an example where Process Explorer is able to open some security descriptor of an object, which represents really all the security or the protection for that object. And the main thing is the DACL. And the way to see that is by clicking the Advanced button, for example. You can see here the ACEs. Each ACE has these triplets. We have the type, whether it's allowed or deny kind of ACE. The user it applies to could be a group like system, account, or other kind of special users. And the access is the access mask. In many cases, you see here the name special. It's not really special at all. It just means that there's no good way to represent that with a single word. If you want to see the actual details, you can click the Edit or View button. Sometimes it's View if you don't have enough access. So you can see here that we actually have a bunch of permissions for this particular object. And this includes the delete bit and the change permission, change owner, a few other things, some of which are generic, some of which might be specific, which I'll get into very soon. This is an example of an access mask behind the scenes. If you look at the same thing using a kernel debugger, you'll find something which is basically the same information, just represented in more kind of raw kind of form. So we can try that as well with this particular semaphore just for fun. Let me launch my local kernel debugger here, WinDebug in a local session. So here goes. Let me just fire up the local kernel debugging session here. Let's give it a shot. And now I can get to the object. So let's go ahead and get to that object. So we can get it using its name or its address. Since we have the address, it's going to be slightly faster. Let's do that. So I'm going to use the object command, if I can type correctly, the object command with the address. And you can see that we have the correct name and all that. And the important part here is that every object has an object header, this object header thing. And this object header is the one that contains the security descriptor, where the access control list, the discretionary access control list, or DACL to be more precise, resides. So if I look at the object header, unfortunately there's no command for that. The only way to do that is just to use the DT normal generic command to look at the structure called object header, which is not officially documented, but it is available as part of the symbols. So I'm pasting in the object header, which by the way is 48 bytes before the actual object. And you can see there's a security descriptor here, right here. So now we can grab this thing and use this SD command to look at that security descriptor. And you get an error. Don't worry about that. It just means there's a bunch of flags here. You just need to turn the last digit to 0, because the lower 4 bits are always 0 for object addresses on 64-bit Windows for alignment purposes. And now we can see the actual security descriptor that has some details, and they're all also presented in Process Explorer, or to be more precise, in the classic Windows security dialog. And you can see here the first ACE, we have this seed, which is 1518, which you might recognize as the system account. So again, going back here to Process Explorer, just to verify, if you go to security and advanced, the order must match. So first we have the system account, then it's my account, and then some logon session ID with some ID account. So we should see the same kind of order in the debugger, and indeed we are seeing that. So the first one is system account. Notice the access mask, that's 1F0003. The security dialog doesn't really show that directly. The only way to see that is to go to edit or view here and see this information using these kind of bits behind the scenes, but it's unclear whether the actual numbers match, but you have to just take my word for it that they do match behind the scenes. And the second one is that user, the seed representing me, my user right here. In this case, it's the same mask. And we can verify that, at least to some extent, by looking at my user here, clicking edit, and we should see exactly the same set of bits that is available here. The last one is the particular logon session ID here. There's something potentially different. So here we have something which looks pretty much the same. This is just an example I've chosen. You can see indeed that all the access masks are exactly the same. And of course, you can do that with any kind of kernel object, see what is going on in terms of the DACL. Anyway, my focus here in this video is on the access mask. So the access mask indicates what can we do with this object in this case, or to be more specific, in this particular case of an ACE, this particular user, what that user can do with this object. So it's allowed to do whatever this set of bits represent. Okay, so what else? What else can we see here in Process Explorer and other similar tools? So before we look at some other, maybe another example, let's go back to the slides and see what access bits or access masks are made of. So here's what that looks like. As you can see, it's a 32-bit value where the lower 16 bits are specific rights, which means these are specific to the kind of object in question. So obviously for process objects, there are different access bits than for a file object, or for a thread object, or a desktop object. Each one has its own specialized bits, and there can be at most 16 bits. There can be no more than that. And then we have a bunch of standard rights, which could be applied to any kind of object almost. So you can see things like these delete access, which means we want to delete the object. This only has meaning for certain kinds of objects, like file objects. There's a read control, which just says that you can read the DACL of an object. If you have write DAC, it means you have the power to write to the discretionary access control list. Basically, you can change who can do what with the object given that power, if you have a handle with that kind of power. Write owner means you can change the owner of the object, and the owner always has the write DAC access mask, by the way. This makes sure that objects can never be completely inaccessible, even if someone by mistake or maybe maliciously changed the DACL in a way that doesn't allow anyone access. Still the owner always has access. And if you have the particular privilege called the take ownership privilege, which by default is provided to administrators, you can in fact change the owner for every object without having that particular bit present there. And synchronize is about the ability to wait on an object until it becomes a signal, whatever that means for that kind of object. Only a very specific set of objects have a meaning for synchronize. For example, process objects can be waited upon. In this case, they become signaled when they terminate. Same goes for threads and other kinds of objects we can wait on, such as events, mutexes, semaphores. But objects that don't have that kind of meaning for that, then you shouldn't really use this access mask, shouldn't exist. Then we have something called maximum allowed. Maximum allowed just indicates that I would like to get the maximum access masks that are available for me, for the caller. If I'm trying to open a handle to some object, I'd like to get the most access I can get without failing. So it basically says, just give me the maximum that I can get. Whether that's good enough what I'm trying to do or not, that depends on what I'm trying to do, but that's one way to go about it, just saying, give me whatever I can get. There's a system SACL here, which I'm not going to discuss. This particular access is for the SACL, is less interesting for our purposes. And the last thing we have here is a bunch of generic things. So we have generic read, generic write, generic execute, generic all. What does that really mean? What happens if I'm asking to get access of generic read? What does that really mean? And so the thing here is that every one of these generic access masks is being translated to a specific write, specific access mask based on the first 16 bits. And so it's a kind of a way to say, you know what, I want a read kind of access, for instance, to an object. What does it actually mean? There is some translation that happens behind the scenes. And this is sometimes used as a shortcut to try to get some kind of access to an object without being too specific, because maybe I'm not familiar with the exact bit. Maybe I don't want to specify the exact bits. I just want to say I'd like that kind of access, a generic write access, for example. So we have read, write, execute, and all. So how can we tell what each of these generic things mean for a particular object type? So this is of course documented, but here's one way to see that. If you look at Object Explorer, one of my tools, you'll find that there's a list here of all the object types that Windows has, and as part of that we have columns here for generic read, write, execute, and generic all. So for example, for a process object, for process objects, if I ask for generic read, what it's actually going to give me is VM read, process VM read, process query information. These are the more specific writes I'm going to get. And of course, that's assuming I can get the handle to begin with. But if I can, generic read means exactly this. So I'm going to ask for that. So it's the same thing if I ask for these things specifically, explicitly, or use generic read. In the case of write, it's going to be something like this. So create thread, that is process create thread, process vim operation, process vim write, process dup handle, process create process. All these things you see here are represented by generic write. So if I use generic write, this is what I'm asking for. It will be converted to the actual specific writes. Same goes for generic execute and generic all. In most cases, generic all just says I want everything, like process all access. So in practice, I would recommend, if you're doing any kind of programming work, it's better to be really explicit and not use generic read or generic write, these kinds of things, because they might ask for more than you actually need. If you ask for more than you actually need, then if you can't get everything, you get nothing. So you want to be as specific as possible. But still, this exists, and sometimes it is useful. If you want to get something generic, maybe you open a handle to various types of objects. Every time it might be a different kind of object, because you're doing something more generic in nature. So you can't really ask for specific access mask. You have to use something more, well, generic, which means something like generic read or generic write. So you're trying to get some information about an object, so you don't know exactly what specific bits to actually use. And so if I take an example here, let's say I would like to terminate a process. Let's say I want to terminate a process. So maybe I have the ability here to get the process ID, for example, similar to the pskill, for example, tool from sysinternals. Let's say that's what I want to do. So in order to do that, I have to open a handle to a process. I'm going to use the Open Process API to do that, as we've done in many other examples in these videos. And as you can see, the first parameter is the desired access mask. This is where I have to specify what do I want to be able to do with the object if my open operation succeeds. And that works in the same way for any kind of object you're trying to gain access to, for an existing object, of course. And so one way to get around to be kind of lazy is do something like this. I want to get a process all access. This is something you can definitely do, at least you can try to do, but this is generally a bad idea. It's a bad idea for two reasons. One that I already mentioned is that you're trying to get something that it's probably more than you actually need. And what happens is that you either get everything or you get nothing. So even if you would be able to get something more specific, less powerful than process all access, you will get nothing if you can't get the entire process all access. So that's a bad idea to do. It also increases the attack surface for that handle, because now that handle, if this is successful, that handle is very powerful. So anyone might be able to try to duplicate that handle to their process and use that. Also, it's slightly slower, because there are multiple bits here to check, so it takes more time for the security system to figure out that you actually have the proper access to get all these bits set up for you. So you always want to be as specific as possible. So in the case of process termination, I want to use process terminate, and that is the only access mask I need. Or maybe I can add another one like synchronize, I want to also wait until the process actually terminates. It might take a millisecond or so, depending on what is going on in that process. Maybe it takes time to close all the handles in that process, to free all the memory internally that the kernel has to do and all that. So let's say I want to also wait until the process terminates. And then I can go ahead and ask for the particular process ID. So I'm going to use the simple a2i function here just for simplicity to grab the first parameter of the command line. If that works, then great, I can do something about it. Otherwise, it has failed and something went wrong. And what actually went wrong is, of course, something we can check using getLastError. But technically, it could be two things. The first one is the more obvious one, perhaps, is that the process ID is junk. There is no process with that ID, and that would be one kind of error, obviously. But then there's the other one, which is going to be access denied, if indeed you don't have that kind of power over that object. For example, if you try to terminate a protected process like CSRSS or SMSS, it's not going to work out for you, even if you have administrative powers, because most protected processes are protected against getting a process terminate access to them. So that's not going to work out. Now, if I do that, and it works, I can use terminate process to terminate the process. That actually has to work. There's really no way this could fail at this point because I have a powerful enough handle to do that. The handle is powerful enough. And then if I want to wait for the process to actually terminate, because it might take maybe a few milliseconds, depending on the state of that process, let's say I want to do that, then I can wait for it. And then I can say for sure, terminated. The second parameter here, by the way, is the exit code I'd like to specify for the process. If I want to get other information, for example, I want to know what is the length of time that the process was running, or what was the create time and terminate time and user time and kernel time, there's this function, getProcessTimes, that I can call. We can provide the handle to the process, and then we can get the various kind of times using this file time generic structure. We can get the create, the exit time, and the user and kernel time, which is just the amount of time that user mode code ran in that process and kernel mode code ran in that process. So we have here the variables we can specify. You can see it's very easy. Just specify the address of those variables, like so. And then I can display that, for example. Do you think this was actually going to work? I recommend you pause this video for a moment and think about it. Will this function work? I'll give you a few seconds to think about it. Okay, so we're back. Hopefully you've paused the video and you have some ideas. So this function is going to fail. Why do you think it is going to fail? And it's going to fail because of an access denied, which might seem very weird, but in fact it's going to fail. If you look at the getProcessTimes function in documentation, it's going to tell you that it requires the handle to have the access mask of process query information or process query limited information. We didn't ask for it, which means we don't have it using this particular handle, and that means this function will in fact fail. So if we do want that to work, we'll have to be even more specific, saying that we actually want also something like process query limited information. That's the minimum one that we can ask for. With that, now this call would work. So the access mask is really critical in terms of what you'd like to do with an object. This example is for a process, but the same applies for any kind of object, really, when you try to open a handle to it. And so for a process, probably wouldn't use something like generic read or write or stuff like that, because it's too much. It's too much, and it's kind of not under my control. I really want to be very specific. It makes sense to use the generic aspects for cases where you might need to open different kinds of objects or get some generic information about objects, and the type of object is not necessarily known in advance. But for specific objects, I would recommend always using the specific, the most explicit ones that you actually need. Be the most efficient to handle, and you'll get exactly what you're asking for, no more, no less. So these are access masks. I recommend you keep looking in various tools and looking for how to see this access mask. And of course, if you're doing any kind of programming, please use them correctly by asking for exactly what you need.